Hi, thanks everyone. Thanks for coming to my talk. So my name is Felix. I'm a security engineer working on Google's product security team. And today I want to talk about a number of vulnerabilities I discovered in popular DHCP implementations. So this is going to be a story about 5 bugs. And I only have 45 minutes, so for most of the bugs, I'm going to concentrate on the vulnerabilities themselves and their impact, but I won't go too much into detail about the exploitation. I have one bug that I use as an example, where I go deep into exploitation and show a live demo at the end, but in the beginning, we will concentrate on the vulnerabilities and the kind of impact they have. So, I assume everyone in the audience has heard of DHCP before, but I'd like to give you this really quick introduction. DHCP is a 25-year-old network protocol, and you use it to dynamically assign an IP address and other config to devices on a local network. And DHCP itself is IPv4 specific, so there's also a successor, DHCP version 6, which is used for IPv6. And it's also 50-year-old already, and almost no one uses it. IPv6 has a feature called stateless address auto-configuration, which is pretty nice. So DHCP version 6 is kind of one of these standards that are not widely used. But it's still supported by all the implementation, as we will see later on. And that's really nice because it offers an attacker a pretty nice attack surface for finding vulnerabilities. So if you look at both of these protocols from an attacker perspective, they look pretty harmless on first glance. So it's DHCP, so it has a reasonably small feature set. The packet format is pretty easy to parse, and it looks like they have a pretty small attack surface they can actually exploit. Of course, it turns out that reality is quite different. Otherwise, I would not be giving this presentation. So, let's talk why would you want to look into DHCP. And first of all, everyone knows you can use DHCP for man-in-the-middle attacks. And it's trivial and it's not part of this presentation. So this presentation is focusing on implementation bugs in DHCP clients and servers. So we're looking for stuff like memory safety issues, code injection vulnerabilities, or file handling bugs. And the goal here is to gain code execution either on vulnerable DHCP clients or servers. And client bugs in particular, so client bugs that allow you to run arbitrary commands on a vulnerable DHCP client, are a pretty interesting attack surface in the real world. So one example where you can use them is lateral movement in local networks. So you compromise one system in a local network, and then you can use this client bug to jump to other systems in the local network that might be more interesting for you as an attacker. Another interesting attack venue are malicious access points. So because every modern operating system will automatically spawn a DHCP client when you join a new Wi-Fi or LAN network, you can easily try to compromise mobile devices like laptops or smartphones just by exploiting a bug in the DHCP client implementation when they join your malicious access point at Starbucks or at an IT security conference. And of course, you can also use them for physical access attacks. So if you have a locked laptop and you have a nice DHCP client bug, you can just physically connect them to your malicious network, exploit that bug to unlock the system and gain access. So let's start looking at DHCP. And I don't want to bore you with a full overview about how DHCP works. And to be honest, most of the stuff is super uninteresting for us from an attacker perspective. Because if you look at the DHCP packet, so the stuff on the right is a DHCP version 4 packet. And if you look at these packets, most of the fields are pretty uninteresting. They have fixed size, so that makes them super easy to parse. They are often deprecated and not used anymore. And most of them are actually just bootp legacy. So bootp is this old protocol that's the predecessor of DHCP. So in practice, if you look at all the fields on the top, no one actually looks at them when you do a DHCP handshake, so we don't care too much. The interesting part about DHCP packets are the options. And options are encoded using a type length value encoding. So for DHCP4, you have 1 byte for the option type, 1 byte for the option length, and then length bytes of the value. And some options are required. So for example, the DHCP message type is actually encoded as an option. And others are completely optional, so you can include them or not. And interestingly, the designers of DHCP version 6 realized the same thing, that options are the only interesting part about this. So if DHCP version 6 packet is actually even simpler because it mostly contains only of options. So I mentioned you have these different option types and option values. And one interesting thing about DHCP is, of course, you can put different stuff in these option values, and the value encoding is completely type specific. So some option types just contain an IP address, for example, the IP address of your DNS server. Others might contain DNS encoded domain names. They might contain ASCII strings. They might contain list of these things. So basically, for all of the option types you support, you need to have the decoding and encoding routines in your implementation to actually be able to parse this. You can also do stuff like you can repeat an option with the same type, and how this is handled is implementation and type specific. So sometimes these values get merged, sometimes only the last option will get parsed, the other one gets thrown away. So makes all of slightly more complex. You also have a nice feature called option overloading. So on the you see these big fields, S-name, server name, and file name, and they're 64 and 128 bytes long. They're not used anymore for the original use case. So what people decided is basically, hey, we can stuff more options in these fields so the space doesn't go to waste. Again, this makes parsing slightly more complex. And then you also have vendor-specific options. And basically, if you want to implement your own feature on top of DHCP, the popular way to do this is just invent your own DHCP option and put stuff into it. For example, Microsoft mechanism for automatic proxy discovery, the WPAD mechanism, is actually implemented on of DHCP option 252, where they just put the URL of the auto proxy discovery mechanism in the option value. So that was the quick introduction to DHCP. Let's look at some code. And the first thing we want to look at is dnsmasq. And dnsmasq is this really surprisingly popular small embedded DNS and DHCP server. And it's used in a lot of spaces or a lot of places you wouldn't really think of. So in a lot of cheap home routers or embedded devices, dnsmasq is actually used for DNS and DHCP. So depending on the quality of your home router, dnsmasq might actually be used in your local Wi-Fi to provide you with a DNS and DHCP implementation. And we looked at this code as the Google security team after we found an initial vulnerability in DNS. And then we did a review of the code base. And this code here is part of the DHCP version 6 server implementation. And if you remember how option works, what it's trying to do is basically it finds the client MAC option, takes the length of that option and stores it in the state maclen variable, and then it immediately puts or uses that attacker-controlled length variable as the size field of a memcopy operation. The destination of that memcopy, so the source of the memcopy is attacker-controlled, it's the option value. The destination is a fixed size stack buffer, so it's a super straightforward stack-based buffer overflow, right, like you would expect to find it in 1998. This was discovered by a colleague of mine, Kevin Hammerer from Google Security. And when he found that bug, I was thinking, okay, so this is dnsmasq, it's somewhat popular, but if bugs like this still exist in these code bases, let's look at the really popular code bases to see if there are like similar issues still there. So what about more widespread DHCP software? And one of the biggest code bases or the most widely used code bases for DHCP is ISC DHCP. And that's the DHCP implementation by the Internet Systems Consortium. They are also well known for releasing the bind DNS server. And the first release of ISC DHCP was in 1997, so the code base is like 21 years old now, and you notice it, so it's not the most modern C code base in the world. And the server side of the implementation is one of the most widely used server implementations. And even more importantly, the DHCP client, called DH-client, is pretty much the default DHCP client on most mainstream Linux distributions. So if you have a Debian or a Red Hat, chances are really high that DH-client is the code base that does the DHCP for you. So the first bug I discovered in ISC DHCP involves reference counting. So for every DHCP option ISC DHCP parses and processes, it has this option structure you can see on the slide. And you can ignore most of the fields here. The only thing we are interested in is the ref count at the bottom. And what the ref count does is basically it keeps track of the number of references in the code base to this option. And if ref count ever goes to 0, the whole structure and all related variables gets freed, and like the option gets thrown away. And normally that never happens. Like most of the time the ref count will be at least 1. But reference counting is permanently done during parsing and processing of DHCP packets. So the interesting thing here about the ref count is that it's a signed 32-bit integer. So you can put quite some references in it, but not infinite many. And if you look how it's used, you have this parse option buffer function. So this basically gets executed whenever ISC DHCP sees a DHCP packet coming in. And it's basically this big for loop. So for every option in the buffer, it will call the option code hash lookup function based on the option type to find like the right option structure. And that function increases the option ref count by 1. It will then process the option, like parse the value, decode it, store it in some global structure, and afterwards it will dereference the option again. So option ref count at the end of this function should be the same as in the beginning. And this is the happy path, so this is the path that the program takes if nothing goes wrong. But I also have this error case. So what happens if like the option length plus the offset in the packet is actually larger than the complete size of the option, right? So this would mean the packet is invalid, we need to error out of it and like break processing. And this is the error case, and it looks pretty good. Like they correctly check for out of bound access, they return an error and return out of the function. The important thing here, what's missing is they don't decrease the option reference counter. So they're missing this call to option dereference that decreases the ref count again. And so this is pretty easy to miss, or it's pretty easy to miss this, but the impact is actually quite interesting. So what happens? Basically you have an attacker, it can be the server or the client in this case, and it sends like DHCP messages with like an invalid option length to your victim, which leads to a ref count that gets increased by 1, right? Because it gets increased but never gets decreased again, so you can increase it by 1. You do that a couple of times. You do that a lot of times. And like after more than 2 billion of these packets, you basically can increase the ref count to the maximum value you can store in a 32-bit integer. And then it wraps around, becomes a negative value. You send even more packages, and at the end, like you go from -2 to -1, from -1 to 0. So you can move the ref count to 0, even though you still have references to that option structure in memory. So the impact of this is that you can turn this bug into an use after free after sending 200 gigabytes of traffic to your victim system. So you can say, yeah, it's 200 gigabytes, that's a lot. Of course, on like a modern LAN system, it's not super unrealistic, right? So if you have like a 1 gigabit or a 10 gigabit connection, this can actually be done in a couple of minutes. But still, it's not the easiest bug to exploit over a Wi-Fi network, for example. So I don't want to go into too much detail how to turn the use of the free into something like an RCE, but basically ISC's option parsing gives you like perfect heap primitives to allocate different sized chunks, free them in an order of the attacker's control. So it's pretty much like if you want to write a heap exploit, ISC DHCP is like a super good target for it. The interesting part about this bug is that it's actually part of server and client. And it happens before any of the other normal checks against packets are done. So if you look at how DH-client listens to different interfaces, it will actually bind to all interfaces and throw away packets that arrive over interfaces where it doesn't expect DHCP traffic. However, because this vulnerability happens before the interface check, you can actually trigger the vulnerability with packets that come from the internet. So on an interface where normally no DHCP traffic should arrive. And so I was able to turn this into remote code execution against the server. Turning it against RCE or against the client is more difficult, basically because it's really hard to turn this bug into an Infoleak against the client, because the client doesn't really reflect values back to the server that much. Okay, so let's go look a bit more. Until now, I only showed you like C code that basically parses options, right? So of course, DHCP does more stuff. So what happens like after a DHCP packet gets correctly parsed is that the new system configuration actually needs to be applied to the system. So like the new IP address needs to be assigned to the interface. And the way DH-client traditionally does this is by invoking a helper tool. The helper tool traditionally is called etc DH-client script. And all the options like the new IP address, the new host name, the new domain servers gets passed as environment variables to that script. The script can apply system configuration and it can also invoke these hooks in the etc DH-client hooks directory. So you can put additional bash scripts in there and they will get invoked whenever the interface changes its state. So now I mentioned that encoding of DHCP options is basically up to the client or like up to the sender, right? So what happens like if you just specify like binary garbage in as an option value? How do they make sure that the value they put into the environment is actually safe? So I mean, you can't put like binary data into an environment variable that would lead to problems. So they need to have some way to make it printable or make it readable. And for this, they have this function, prettyprint option. And prettyprint option, the whole idea of that function is basically to turn a binary garbage option into something that a human can easily read. So this function supports integers, it supports IP addresses, it supports strings. For strings, it correctly encodes and decodes like special characters. And it also supports binary data. So if it finds, or if it discovers that this string contains something that's not printable, it will actually just convert the whole string into an hex-encoded string and pass that by the environment variable. So if you look at this function and you see this pretty big local static buffer variable called opbuff, which has space for 30,000 characters, I mean, that's a good sign that there's probably something wrong here, right? Interestingly, the XXX comment behind that variable definition was actually in the original source code. So I guess the developer, when writing that, already assumed that there might be something wrong with it. And looking at it, it turns out they basically don't have any boundary checks. So if you have just like a really large option value that gets encoded into its hex form, you can easily override that buffer because they never do any boundary checks. And again, you get a pretty straightforward buffer overflow. So this bug isn't triggerable over DHCP version 4 because packet sizes are not long enough to actually put such a long option in there, but it can be easily exploited using DHCP version 6. So now I said DHCP version 6, no one uses it, right? So in the beginning I thought this makes this bug pretty uninteresting. But it turns out that ISC DH-client on modern systems actually automatically gets spawned with support for DHCP version 6 if the right packets are in the network. So how does this work? So the last slide with the simplified architecture was basically not true anymore. So on a modern system, the architecture looks like the following. You have network manager. And network manager, when it sees a new network connection coming up, it will spawn a DH client. If it sees router advertisement packets, so IPv6 router advertisement packets that specify stateful configuration, it will spawn up a DH client that supports DHCP version 6. So as an attacker, you can easily trigger DHCP version 6 clients by just sending the right router advertisement packets over the network. So the DH client still does its thing and invokes a helper script with the environment variables. But this isn't a bash script anymore. Instead, the network manager has this helper utility called nmDHCP helper. So this gets invoked with all the environment variables. And nmDHCP helper does only a thing. It sends a dbus message back to network manager, passing all the option values it got back to network manager. So network manager again can do its system configuration, apply system configuration, and of course it also needs some way to hook into or to allow for extensions. So if you want to extend network manager with your own scripts, they have a mechanism for this. And again, there's a magic directory where you can put bash scripts in, and it's called etc network manager dispatcher D. And you can put shell scripts there again. If network manager changes or the interface configuration, it will invoke these helper scripts. There is only one problem. They decided they actually have different environment naming scheme. So instead of having the option name something like new domain servers for a new domain servers option, they name it DHCP version 4 domain servers. So basically, you can see on the left side, you can see the new version. On the right side, you can see the old version. And you can see the naming scheme is slightly different. Which is a problem. Like if you have, imagine you have this super complex environment and you have written a lot of these DH client hook scripts that do like all kind of fancy configuration stuff. You can't simply copy them over into etc network manager dispatcher D because the naming scheme doesn't fit. That's bad for backwards compatibility. So engineers at Red Hat decided to write a helper script that solves the problem. So this is a script that's in the new dispatcher directory, and it's responsible for running all the old style hooks in the old directory. It's called 11DH client. It's used by default on Red Hat Enterprise, Fedora, and CentOS, and is always used. So even if you don't have any of the old style hooks. And the only thing 11DH client needs to do is it needs to translate this new naming scheme back to the old version. So it needs to translate DHCP 4 underscore option to new underscore option. So how are you going to do that? Of course, you have a giant eval block in your script. So if you look at this, so this runs every time you do like a network configuration using network manager. And I mean, just looking at it, and you see this big eval on the top, you see this it doesn't look like a good idea, right? So what happens here, or what are they trying to do? So basically, they call the declare command, which prints out all environment variables for the script. Then they use grep to filter out everything that's not an DHCP environment variable. So they only look at stuff that starts with DHCP 4 underscore. And then they read those values line by line. And then the block inside this while loop basically just splits option name and value, lower cases the option name, replaces the DHCP 4 by new, puts the stuff back together again, and then calls echo with export, new name, new value. So how does this go wrong? Basically, it's vulnerable because of the following change. They invoke read without the -r flag. And read with, so this is the patched version of the script. The only difference is this -r behind the read comment. And the reason for that is if you invoke read, the read built-in without this flag, it actually eats backslashes. So this means if you send over a variable like foo single quote, which gets correctly escaped by the declare comment into foo backslash single quote, readr will remove the backslash. So at the end you have foo single quote. And this removes the required escaping for the option values. Because as you see, at the end, they echo that inside an eval block. So what they need to do is they need to make really sure that opt value is correctly escaped as a single quoted string. This doesn't work anymore because of the wrong invocation of read. So the eval block becomes vulnerable and you can inject arbitrary comments. And the impact of this is that you can get remote code execution on any vulnerable system by sending, as a malicious DHCP server, as sending some option like the wpet option with a string like foo single quote and then followed by the command you want to execute. And this vulnerability, so this is again like, it's relatively simple, right? It's not super highly complex, but this vulnerability gave you remote root code execution on vulnerable Red Hat systems for the last 5 years. So you could basically go through most enterprise networks and own every system you see. It also, by chance, it got a really nice CVE number, so it got CVE 1111, which I really enjoy. And some people even decided to create a logo and a song for it. So if you want to listen to the vulnerability song, you can go to dinoroot.ninja and listen to it. So this was Network Manager. And systemd developers decided to write a Network Manager replacement under the systemd umbrella. It's called systemd networkd. It's included in the default installation of Ubuntu 18 and also on some Red Hat Enterprise Linux images and container distributions. And it follows the systemd strategy of writing everything from scratch. So it has no dependencies on external DHCP clients like the H client. Instead, they wrote their own self-written implementation of DHCP in modern C as a completely new rewrite. And the idea is it doesn't contain any historical baggage. Instead, it's like a fresh implementation, so everything is going to be great, right? Of course, it's written in C, so it's easy to make mistakes. So this is the next bug, or this is the last bug I want to talk about. And so this happens when systemd networkd tries to build a response packet it sends back to the DHCP server. And they append something to this working buffer of the response packet and try to make sure they have enough space. So they check, so this function gets called with a buff argument and bufflen argument. So buff is the response buffer of the packet that they're building. Bufflen is the remaining size of that option buffer. And what they're trying to do is they try to check that the stuff they're going to write in the response buffer actually fits. So they have this check where they look at bufflen, and if it's smaller than the length they're expecting to write, they will return an error and don't write it. However, they made it pretty easy to make a mistake. This length check is incorrect. So this is the fix again. It needs the size of this DHCP option header, so option type and option length. Because otherwise you can see basically they decrease bufflen not only by length, but also by the size of the DHCP option header. So this makes bufflen underflow. It's a sized integer, so it becomes like a really, really large 64-bit integer. And this allows you to, as an attacker, to have a pretty controlled heap out-of-bound write. And again, the vulnerable code here is part of the DHCP version 6 functionality. However, it's enabled by default, and systemd networkd even has the property that they will enable DHCP version 6 even if the administrator disables it in the configuration. So you can say, hey, I only want to support DHCP version 4 on this network interface, But if systemd sees a router advertisement packet that looks like it requires DHCP version 6, it will happily enable the DHCP version 6 functionality and go with it, and overwriting the setting you enabled in your configuration file. So let's talk about how you can turn this heap corruption into remote code execution, so to actually get a shell on a vulnerable system. As I said, to summarize the bug, it's a pretty controlled out-of-bound write in a fixed-size heap buffer. And the target system I want to focus on is an Ubuntu 18.4. That's the long-term stable release, still pretty recent, so this is something that you can probably find. We are, of course, looking at the vulnerable version of systemd as it's included in this Ubuntu distribution. Ubuntu 18 also has a pretty recent version of glibc, which becomes relevant for the heap exploitation. And it's a modern distribution, so it's reasonably hardened. This means you have a full address space layout randomization, and the systemd binary is position independent. So you don't have like any easy tricks that make this memory corruption trivial to exploit. We have one big advantage because it's a systemd service. If you trigger the memory corruption and do something wrong and the service crashes, systemd will immediately restart it. So basically we have infinite tries. If we do something incorrect, we can just try again and hope that it works this time. So to turn one of these bugs into remote code execution, you basically require some way to bypass or to break RSLR, address-space layout randomization. So you need an Infoleak. Fortunately, the same version that I found the bug in also contains another bug that was silently fixed by the developers later on. And it's pretty much the perfect Infoleak. So this is again a function that parses the DHCP option, as like every function I showed you so far. And what they're trying to do here is, if you get a packet and it specifies an option length, like includes an option with an option length, they actually want to make sure that the option length fits into the remaining bytes of the packet, right? Which makes sense. Otherwise, it's an out-of-bound option. And they have this check where they check that the complete length of the packet they are getting is large enough to actually hold the option length. However, the mistake they are doing, so they're iterating over this, and the actual position in the packet is in the pos variable. And if you look at that if check, the pos variable, the position, is never taken into account. So the correct code for this check would look like this. They would actually need to check that from our current position in the packet, the remaining length of the message buffer is still large enough to contain the option length. Because they never take the position into account, as long as the complete message is large enough to fit an option, they think it will fit even if the option is right at the end of the packet. So how can you trigger that bug? Or how can you turn this into an usable Infoleak? And the idea is basically something like this. As a malicious server, you send a DHCP version 6 packet that contains some random valid options. You don't care about them, they're just there to fill space. And then right at the end of the packet, you include an additional option. And this one has an invalid length. So it's the option type server ID. And we say, hey, this option is 150 bytes long, but in reality, it's only 1 byte long. And what systemd will do, so server ID has the interesting property that the client will reflect it back to the server in the next packet. So the next packet you get back from the client will look like this. It will include the option, server ID option, and it will include the option length of 150. In addition to the 1 byte you pass to it, it will include 149 more bytes that are leaked out of the systemd memory. So if you are familiar with Heartbleed, this is like it's pretty much the exactly same bug. So we can use this to read memory or leak memory of the systemd process. How do we turn this into something that we can use? The idea is we want to leak a pointer that points at glibc memory. I'll talk later about why this is super helpful for us, but basically if you have a glibc pointer, you can bypass RSLR and go on with your exploitation. And if you look at how this memory layout normally looks like on the heap, you basically have this green chunk is our heap chunk that contains our DHCP message. And underneath it, or behind it, comes the next chunk. If that memory chunk is a free chunk, and if it's a free chunk that's stored inside an empty glibc bin, like a free list, or the small bin or large bins, then you actually have this metadata stored on the heap. So the forward and the backward pointer of a linked list. And if these forward or in many cases, in a freshly started process, this forward and backward pointer will actually point to an address inside glibc, so into a data structure that's inside glibc, which is called main arena, and some offset of it. So what we can do here is, if we have this pointer to main arena plus the offset, we can actually, out of that, we can easily calculate the base address of glibc. If you have the base address of glibc, RSLR is broken for most practical attacks. So we have solved this first problem. And of course, this desired heap state might not always exist, but chances are pretty high that this is how it looks like when systemd is freshly started and just processes its first packet. And what we can do if it doesn't work out, we just continue doing it, or trying to do it, by crashing systemd and looking at it again. So you can actually have a super simple heuristic where you just check that the forward pointer and the backward pointer is the same value. If it's the same value, you know it's a pointer to glibc. So now we have a heap overflow, we have an Infoleak, and we want to get to RCE, we want to turn this heap overflow into an arbitrary write. And so the difference is basically, at the moment we can only write attacker-controlled data at the end of our buffer or after the end of our buffer, but we want to turn it into a primitive that allows us to write attacker-controlled data at any address we are choosing. And so of course, this is something a lot of people have tried to do with a lot of vulnerabilities. There's a lot of cool research about it. There's the different techniques. And one way to do it is basically you want to manipulate the glibc malloc metadata in a way that the next call to the memory allocator will return an attacker-controlled address. This is great. Like if you can trick malloc into allocating an attacker-controlled address, you can trigger something like, "Hey, I'll send you a new packet of the following size," and the payload of that packet will actually be allocated on an attacker-controlled address. So we get an arbitrary write. And there are techniques to do this against every version of glibc. They're called House of Spirit, House of Law. Different complexity might not work always. However, if you have a recent version of glibc, like a modern one from the last 2 years, doing this or tricking glibc into returning an arbitrary attacker-controlled address is actually much easier. And there's a new approach how to do this. It's called tcache poisoning, and it works thanks to some awesome feature called tcache. So tcache is a thread local cache for recently used memory chunks. It was introduced in some recent glibc version, and you can see this in my slides. I linked to a blog post that goes into much more detail about the mechanism. But basically, what happens here is it tries to speed up all these memory allocations and freeze by having like another cache layer where the last 7 chunks for every chunk size are stored in a singly linked list. And it's a last in, first out data structure. So the last chunk of a specific size you freed will be the first one you get back when you allocate the exact same size again. And the super interesting property, or depressing property, depending on how you see it, is that tcache doesn't have any integrity checks. Like normally what glibc malloc tries to do, if it follows pointer or does like these metadata operations, it will actually check that this value it operates on makes some sense. And it was added after everyone noticed, hey, these heap exploits are pretty trivial to do. tcache, which was added 2 years ago, basically doesn't have anything of that. So if you have a recent glibc and you have tcache, you can actually easily exploit most heap corruption vulnerabilities. So super quick intro how tcache works. Imagine you have this tcache data pointer at the bottom of the slide. It links to a chunk B. Chunk B links to D, chunk D links to E, so this is the tcache linked list data structure. How it's stored in memory, you see on the right side of the slide. So you have, for a malloc chunk, you have this chunk size, and then you have a tcache next pointer that points to the next chunk in that linked list. And if you allocate something, so you allocate a buffer with the correct size, it will allocate the buffer B, or it will return the address of the B buffer, and the linked list will change. So now the pointer points to D instead of B. And if we do it another time, then of course we get D back, and now it points to E. So pretty simple, nothing spectacular. So what happens if we do tcache poisoning? So now we have a heap-based buffer overflow of the chunk A. We trigger the overflow so we can corrupt chunk size and tcache next pointer of B. And traditionally, you actually needed to have some approach to like write the correct chunk size in there and make the address you write into tcache next or into the next pointer to look somewhat realistically. For tcache, you don't need that. You can just trash chunk size with any value you want, and then you put your target address, the target address of your arbitrary write, into the tcache next pointer. So this is how it looks like afterwards. And of course, our first allocation still correctly returns the address of B, but then our second allocation returns the address we overwrote. So now we have this arbitrary write primitive after a heap overflow. We have an arbitrary write and we have an Infoleak, how to get remote code execution out of this. And if you ever played a CTF, this is pretty much the way most people do it. It's quick and dirty, but it works for us. So there's a function pointer inside glibc, which is called __free hook. And this hook pointer is called every time the glibc free function is called. If we override that pointer with the address of the system function, so the system function is the one that executes comments, then every time when a memory address is freed, glibc will actually call system with the first argument being the address of that memory address. And if you are able to trigger a free of an attacker controlled chunk, this immediately gives you code execution or command execution. So, putting the whole chain together, you basically start in a network. You have a systemd network client that you want to exploit. You trigger the DHCP version 6 functionality by sending the right router advertisement package. Then you use this option size out of boundary to leak a pointer to glibc, calculate the libc base address. You trigger the heap override, perform this tcache poisoning to turn it into an arbitrary write. You can allocate a fake chunk at the address of free hook and write the address of system to it. And then if we can trigger a free of any chunk where we can control the payload, you get a shell in it. So I have a super quick demo to see how this looks like, if it works. It's a recorded demo, so I'm sure it works. You can see basically I started the exploit, and it starts by creating a DHCP version 6 server, and it will ignore the first couple of packets it gets from systemd, just to make sure the heap is like in a reasonable state, and we don't get into like any race conditions. So then what after it decides to actually start the exploit, what you can see is some DHCP version 6 packets being exchanged, and we trigger the actual Infoleak. And you can see this got server ID right in the middle, where we got a server ID that contains a memory leak, and out of that leaked server, we can read out the chunk header. And you see the chunk header basically has the size value, and then it has like these two pointers at the end. And these are the pointers to libc. Based on these 2 pointers, we can calculate the libc base address, which also gives us the address of freehook and the system function. So we have this Infoleak, we have everything ready to go, so we can trigger the tcache poisoning and hope that it actually executed our commands at the end. So the exploit finished. Now I try to connect to a port on the systemd system, and you can see I get a shell. It's running a systemd network. So this is the user systemd network runs. So it's not a root exploit. You don't get root privileges immediately, but you run it as the systemd network user, which is, it's slightly sandboxed, but still pretty powerful. So it gives you like a good access to the system. Okay. And with that, it's basically, I just have a quick conclusion to this whole presentation. So if you look at DHCP, at first glance, it's pretty simple, but if you look at how it's actually implemented, you see reality is different, as it's often the case. So even if it looks like a small attack surface and no one is going to have exploitable bugs in DHCP, I actually found 5 of them in a relatively short time frame. It's one of the cases where you have a functionality that no one uses, like DHCP version 6, but all the implementation still heavily supports it. And of course, as always, you have this problem of having backwards compatibility that actually increases complexity of the system and heavily increases the attack surface. So this was the shell injection vulnerability you saw, where basically just for reasons of backwards compatibility, we add these weird features that make stuff exploitable. And finally, if you have a sufficient powerful memory corruption, like a heap out of bounds write and an Infoleak, you can still turn them to RCE. So some people argue, hey, a lot of these bugs are not exploitable, but if you actually invest the time, you can still do this and get shell out of these bugs. And of course, for that reason, please don't write new network daemons in C. I really like systemd's approach or idea of implementing a lot of this stuff from scratch to like remove technical debt. But if you have the engineering headcount to actually do new implementations of this stuff, you shouldn't write it in C. You should take your engineer and let them write it in a memory-safe language. You can use Golang or Rust for it. For something like DHCP, which is not really performance critical, you could even write it in Python, and you wouldn't see like a performance degradation of your system. So yeah. If you take one sentence away from this presentation, let it be, please don't write new network daemons in C. I think that would make everyone very happy. That's it. Thanks for listening.
Any questions from the crowd? Anybody, any questions? Going once, going twice. And that would be it then. Thank you so much, Felix. That was an amazing presentation.